of the lesson. Okay, page 20, June 18, P41. Let's go through that. June 18, P41. Question. What question is this? This is question 3. Okay, so what is meant by internal energy of a system? This is again the definition question which I already mentioned last week. You just need to say is the sum of a random distribution of kinetic and potential energies associated with molecules of a system. Okay, so 2 keywords here. You need to have mention of random. You need to mention that it is the sum of kinetic and potential energies of molecules inside a system. If you just say it's the sum of kinetic energy and potential energies, that one is actually not complete. You have to make mention that the kinetic and potential energy is relating to the molecules and that the values are random in the first place. Okay, so that one should be fine. Okay, so that one is just a definition issue. Okay, now for part 2, have a look at part 2. It was mentioned that here, explain why for an ideal gas, the change in internal energy is directly proportional to the change in thermodynamic temperature of the gas. Okay, now thermodynamic temperature, this one, if you're taking chemistry, this one you already should know is actually talking about temperature in Kelvin. Okay, and then another keyword here is that they mention ideal gas. They're asking you to explain why is it that for ideal gas, internal energy is directly proportional to temperature. In other words, why is it like this? Why is it that for ideal gas, internal energy is proportional to T? Okay, so this one you can actually do it from a few ways. You first need to remember that internal energy is the sum of kinetic energy and potential energies of molecules inside a system. Okay, and then after that, from here, we know that for ideal gas, there's no intermolecular force. Therefore, no PE. So this equation that we have originally will become internal energy is just equals to kinetic energy of your molecules. This is the conclusion you can get when it comes to ideal gas. But then you have to relate it to temperature. So this one, in order to relate it to temperature, you have to make use of something that you will learn in ideal gas chapter later on. In chemistry, you may have already learned this, but in physics later on, we will learn this again under a chapter called ideal gas. So what we will learn eventually is that kinetic energy of molecules is actually proportional to temperature. Now, the reason why we say it like this is because later on you will actually learn a particular equation which says this. Ke is actually 3/2 kT, where K is a constant called Boltzmann constant. But this one you will learn later on. The gist from this, the conclusion from this is that from this equation, you're supposed to be able to deduce that Ke is proportional to T. Okay, so this is one other fact that you will need to know. If I tell you that this is equation 1 and this is equation 2, if you relate these two together, relating equation 1 and 2, if internal energy is equal to kinetic energy, and then kinetic energy is proportional to temperature, the conclusion that you ought to be able to get is this. You should be able to say that in the first place, internal energy is proportional to temperature, if you relate both of these relations together. Okay, so this is what the explanation is actually supposed to tell you. Okay, in equation form it's easier to see, but in word form, like the ones that are written in your answers here, is a bit difficult. Okay, but the points are still there, all right. First, you need to say that an ideal gas has no intermolecular forces, so it has no potential energy. Therefore, internal energy of an ideal gas is just solely the kinetic energy. And then mean kinetic energy of particles is actually directly proportional to thermodynamic temperature of gas. So therefore, internal energy is directly proportional to thermodynamic temperature of the gas. Okay. This last statement here is actually not required for you to write. It's not given any marks. The ones that are highlighted in green are the ones that actually have marks. Okay, right. Sorry, I noticed my mic is a bit far for me just now. Could you guys hear me properly just now? Can you guys hear me properly, right? Okay. I just noticed that my mic is actually not in front of me, it's actually towards my side. Okay, so if you can't hear properly just now, just let me know and then I'll just repeat some of the stuff that I just said. So if you all can hear me properly, I think that should be fine. Okay, so this is for page 23A. Okay. Okay, there shouldn't be anything after this. All right, then after that, we move on to the next question, page 16. Okay, wait on, let me just clear all some of the stuff here. Okay, the next one we'll go through is page 16. Okay, let's have a look at page 16. Okay. Okay, page 16. Page 16 is actually the middle part of the question actually. It should have been page 15, sorry. Okay, have a look at page 15 of your worksheet. Okay, so let's have a look at page 15 of your worksheet. Okay, this one is talking about March 17P42. You know, let me just go to March 17P42. Okay, so here they tell you one thing. Yeah, let me just erase something here. Okay, sorry. Okay, the question states that the first law of thermodynamics can be represented by the expression delta U equals to Q plus W. What is meant by the symbols in the expression when we say there's positive delta U, positive Q, and positive W? So remember in the notes last week, I mentioned to you that for these three variables, positive and negative have a specific meaning to them. If you are talking about positive delta U, it means increase in internal energy. If you're talking about positive Q, that means heat is transferred to the system, or rather heat is supplied to the system. And then if you're talking about positive W, this one means work is done on the system. Okay, specifically when it comes to work, the keyword is either work done on system or work done by system. Okay, so this is something that you just need to come into memory lah. And then after that, your explanations will become much easier to do. Okay, now part B. Part B is asking you right now, a fixed mass on ideal gas. You see again, they mentioned to you that this is an ideal gas. So a lot of times try to search whether this keyword is that. Okay, so a fixed mass of ideal gas undergoes a cycle ABCA of changes as shown in this figure. During the change from A to B, energy supplied to the gas by heating is 442 joules. Use the first law of thermodynamics to show that the internal energy of the gas increases by 265 joules. Okay, so if you look at the keywords here, there are some keywords you can actually identify from all of this. Okay, first one being they tell you energy supplied to the gas by heating is 442 joules. This one by heating, energy supplied to gas by heating. This one already means delta Q is plus 442 joules. Okay, it's supposed to be a plus in the first place because heat, you are supplying heat to the system. Okay, then they ask you use thermodynamics first law, which is basically this one here. Delta U is equals to delta Q plus delta W. Show that the internal energy of the gas increases by this value, plus 225 joules. Okay, so you're supposed to use this equation, which is what you find in thermodynamic first law, to show the internal energy increases by 265 joules. Okay, so you already know that delta Q is actually plus 442, but you're just missing the work done. Okay, so the process that I'm describing to you here is actually from A to B. A to B is this one. Okay, notice that from A to B, there's actually a change in volume at constant pressure. Okay, this is a horizontal line. If it's a horizontal line, you see that the y-axis here right now is pressure. So it went from A to B, is a horizontal line. The pressure actually never changed. But when you look at the x-axis, your volume actually did change from here all the way to here. Okay, so there's a change in volume at constant pressure. This one tells you can actually find out the work done by the gas. So last week I mentioned to you, work done by gas is actually pressure times change in volume. This is similar to what you've learned in your AS physics last level. Okay, so your work done can be found by taking the pressure times the change in volume. Okay, now from here, there's just one thing to note. Is my work done going to be a positive value or negative value? Or rather, is my work being done by the gas or on the gas? So you have to look at this one. If you're going from A to B, what can you say about the volume? The volume is increasing, isn't it? You see, from A to B, your volume is increasing. So if you see that your volume is increasing, let me use a different color. Oh, okay, now your volume is increasing. That means work is done by the gas. Therefore, delta W is negative. Okay, so you can use this equation to find out the magnitude of the work done. But as to whether it's going to be a positive or negative, you have to see how the volume is changing. Is it a volume increase or is it a volume decrease? If the volume is decreasing, it is work done on gas. This one is actually stated somewhere in the notes, somewhere around page 4 of your notes. Okay, so but here is the other way around, is volume increase. So work is done by the gas. So work is negative. Okay, so all you just need to do now is to find out what is the work done. So there are a few things you can do. You can probably do something like this first. You can first start off by writing the magnitude of the work. Calculate the magnitude of work done. Pressure times change in volume. The pressure is 5.2 times 10 power 5. The change in volume is from 1.6 to 5. So take the difference. Don't forget the power of 10 inside. You're going to get the answer as 176.8 joules. Okay. Now from there, you can actually try to explain whether it's going to be positive or negative. So gas is expanding at constant pressure, or rather you can just say that volume is increasing at constant pressure. Therefore, work is done by gas. It is negative work. Okay, this one is going to be a negative when you plug inside thermodynamic first law. Okay, so you look back at the thermodynamic first law, which is this. This one is following the equation that is given up at the top here. All right, at the top of your question. So I mentioned to you that heating will be positive, 442. Your work done will be a negative. So it's negative 176.8. You add those two together, you're going to get 265.2 joules. Round it up, you will get 265 joules. Okay, so this is how you go and do your existing question for this one. All right. So be careful about your positive and negative when it comes to work done. Okay, so if this one is okay, then let's look at the next part. Next part is actually something that you may have done before last week. Actually, you've done it before. That one is the next question, sorry. Okay, now they tell you that during the change from B to C, internal energy of the gas decreases by 313 joules. Now, by considering the molecular energy, state and explain qualitatively the change, if any, in the temperature of the gas. Consider the molecular energy, meaning to say consider the energy of the molecules in terms of Ke and Pe. Okay, this one is really implying to you in terms of the Ke and Pe of the molecules. Okay, so explain qualitatively the change in the temperature of the gas. Qualitatively just means you describe how it changes. You don't need to do any calculation. No calculation, no values required. Okay, so how are you gonna describe the change in the temperature of the gas? Because here you say that internal energy decreases by 313 joules. How would this affect temperature of the gas? Okay, so this one actually will, the explanation will follow back what we have here. I mean, the understanding is following this. As I mentioned to you, internal energy is Ke plus Pe of molecules, but for ideal gas, no IMF, so no Pe. So internal energy is just Ke, okay? But at the same time, kinetic energy is given by this equation, which you will learn in the next chapter. But just note that Ke is proportional to temperature here. So this and this, if you relate them together, will tell you that internal energy is proportional to temperature, okay? So if you really know this little relation here, if you know IE is proportional to T, this one will in turn tell you that if IE is dropping, temperature obviously will drop. Okay. Here you know IE is dropping, internal energy is dropping, because here they already told you internal energy of the gas decreases by 313 joules. So you know it is dropping. Okay. So you just need to kind of make the relation first. How is internal energy related to temperature? So you notice the explanations are more or less the same. You always say ideal gas has no intermolecular force or no molecular potential energy because intermolecular forces are negligible. So when internal energy decreases, total kinetic energy decreases. So when kinetic energy decrease, temperature decrease. Yeah, this one I think is based on. Okay, this one again is a bit different from what I just wrote here. This one is based on this. Sorry, wait, let me just try and make sense for you. IE is Ke plus Pe. So ideal gas has no intermolecular force, therefore no Pe. So internal energy is just equals to Ke. Then after that, this one they tell you if IE is dropping, Ke should be dropping. Okay. Then after that, what happens to number 2? Number 2 is this one. Number 2 is Ke equals to 3 over 2 Kt. Ke is proportional to T. So if Ke drops, T drops, no? Okay. This is another way of looking at it. Okay. This one is doing step by step. This one is like combining everything and making the conclusion. Sorry, I have a tendency to always do this, but the answer that is written somehow is always talking about this. Okay, but it's the same thing now. It's just the ordering of the answers that are a bit different. Okay, so the ones that are written in pencil here is more related to this order of explaining things. You start with IE equals to KE plus PE. Ideal guess there's no IMF, no PE, so IE is just KE. When IE drops, KE drops. Okay, and then after that, since KE is proportional to temperature, when KE drops, temperature drops. Okay, now when you look at the answers, you'll notice that certain things are not mentioned. Like say, for example, we never say that internal energy is equals to KE over in the answer. And neither did we say that KE is proportional to temperature inside the answer. But somehow we straight away assume we how to say, if you look at the answers here, you'll notice that certain points are not written. Okay, the complete understanding is step by step, this one. Okay, but you notice that when you write the answers, certain things are omitted. Like say IE is equals to KE, we never really said that. And then KE is proportional to temperature. We also never really said that. It's understood that you already know this. That's why it's omitted inside. Okay, but if that's the same in the exam, you're just not too sure whether you should write it or not, just write it in. Okay, you never know whether it's given any marks or not. All right, so if you're not sure, just write it in. Just write the full complete explanation. All right. Okay, so this one should be okay. Right, then if you just look at part 3, the change for the change from C to A, use data from B1 and B2 to calculate the change in the internal energy. All right. So from C to A, what is the change in the internal energy? Okay, so let's just go through this one. This one actually is something that you've done from last week. Okay, the one that from last week actually was a bit clearer in the sense that they give you a hint on what they want. All right. If you look at the same diagram again, this little diagram here, this one is a closed cycle. Okay, you'll notice that your gas started from A, it went to B, and then it went from B to C, and then finally it went from C back to A. This is a closed cycle. All right. So you could say that when it went from A to B, there was a change in internal energy from A to B. There's also a change in internal energy from B to C. And then lastly, there's also a change in internal energy from C to A. Okay, so if you are talking about the change in internal energy of the whole complete cycle, you would actually be able to say this, where we say that the change in internal energy of the cycle is actually delta UAB plus delta UBC plus delta UCA. What you want is this one, change in internal energy from C to A. Okay, but this one can only be found if you know what are the others. All right. Now, you should realize that the change in internal energy of the entire cycle is actually going to be 0. Okay, because we know this relation here. You know, if you look at this part here, after all the little derivation, you should know by now that ideal gas is proportional to temperature. Okay, if you go from A to B to C back to A, temperature is unchanged. Therefore, IE is also unchanged. Okay, internal energy will also be unchanged here because temperature did not change in the first place. if you consider the whole cycle. This one, A to B to C to A, is actually the whole cycle itself. Okay, so the internal energy is unchanged. This one will already tell us that delta U for the entire cycle is actually 0. Okay, so this one we know already. This one will be 0. But what about the change in internal energy of AB and change in internal energy of BC? You actually already know this. You see, they ask you to use data from B1 and B2. If you look at B2, they already tell you internal energy decreases by 313 joules. So the fact that this one is a decrease for change from B to C, this one already tells you delta UBC is going to be negative 313, indicating it's a decrease. And then you look at from A to B, from the previous page, you already proved that the internal energy is increasing by 265 joules. So this one is delta UAB equals to plus 265 joules. Okay, so you actually already know the values already for UAB and UBC. So UAB is 265, UBC is negative 313. From here, you can actually find out delta UCA already, which by right should give you just 48 joules. Okay, so it's just 48 joules. Right? Yeah, it's just 1 mark. I mean, the explanation, the understanding behind it seems to be a bit long-winded, but you see, this entire thing is just 1 mark. Okay, you're supposed to have some prior knowledge that internal energy of ideal gas for a whole cycle is actually 0. Okay, so all these little explanations that I've written here is just to let you know the full step. Okay, right, so for closed loop, total change in internal energy is 0. Delta U of whole cycle is UAB plus UBC plus UCA equals to 0. So sub everything in, you will get UCA as 48 joules. Just like that. Okay, right, so this one should be quite straightforward. Do you guys have another question here? Yeah, you guys have another question here. Okay, right. There's another question after this. This one is actually from your ideal gas chapter, but I think since you guys have taken chemistry before this or currently taking chemistry, you should be able to do this. Okay. They tell you right now that the temperature of the gas at point A is 227 degrees centigrade. Calculate the number of molecules of a fixed mass in a fixed mass of gas. So this one you can actually just use PV equals to nRT. You know the pressure at A is 5.2 times 10 power 5. The volume is 1.6 times 10 power minus 4 meter cube. The molar gas constant is 8.31. And then your temperature is in centigrades, degrees centigrade. You just need to change it to Kelvin by plusing 273.15 Kelvin. Okay. Now you can either just, this one is changing from degrees centigrade to Kelvin. Okay. Now this one, you'll notice that usually before this, you always plus 273, right? To change to Kelvin, but somehow here I wrote plus 273.15. You can use either one. You can either use this one or you can either use this one. The reason why I use this is because the conversion to Kelvin, the syllabus booklet mentioned to plus 273.15. Okay, that's the only reason why I put it inside here like this. Okay, but in the marking scheme, if you just plus 27, in the marking scheme, actually they don't use this. In the marking scheme, they actually use plus 273. So it's a bit odd. The syllabus booklet says that when you want to change from degree centigrade to Kelvin, you plus 273.15. But in the marking scheme itself, if you look at how they go and change the temperature, they just use plus 273. Okay, so actually both are acceptable. It's really up to you. In my case, I just follow the syllabus booklet. Right, in the first place, you plus the only difference here is the 0.15 here. The 0.15 actually won't even be reflected inside your answers most of the time. That's why I can say that you can just use 273 itself. Okay. Right. So eventually, if you solve this using PV equals to nRT, you should get the number of moles as 0.020. Okay. So the question wants number of molecules. All right, number of molecules. In chemistry, you would have learned that number of moles is number of molecules over your Avogadro constant. Okay, so maybe I better just write it here since this is probably the first time you're seeing this. The N is number of molecules. The Na is a constant called your Avogadro constant. Okay, which is 6.02 times 10 power 23. So this N here is actually your number of moles. Okay. So number of molecules is number of moles times Avogadro constant, giving you 0.02 times 6.02 times 10 power 23, 1.21 times 10 power 22. Okay. This is your number of molecules. Okay. Your Avogadro constant and your molar gas constant that you've been using here, this one, if you don't remember, don't worry, it's actually given in your syllabus booklet. Sorry, not syllabus book. It's given inside your data sheet for your exam. Okay, under page 2. You will see your molar gas constant as this one, 8.31. Your Avogadro constant as this one. Okay. So even if you don't remember it, it's fine. You can always relate. You can always refer to it from your exam sheet. Okay, right. So this question should be okay already. Wait now, wait. Go back to that. Okay, right. So this one is okay. Then after that, I'll move on to about 4 more questions. Okay, if this one page 20 is done, sorry, we've done page 16. Next one is page 1. Okay, let's move on to page 1. Okay. If you guys move on to page 1, it's June 15 P41. Let's move on to that. June 15 P41. The first question is still talking about what is meant by internal energy. So this one you can actually just kind of skip it. Right, you already know the definition. It's the sum of a random distribution of kinetic and potential energies of molecules in a system. Okay. Now what I've written here on the screen is different from what you have in the notes. Okay. But they're still talking about the same thing, all right? So the ones that you have in your notes, this one is actually the more consistent one. Okay, this one is the better one. All right, if you use this answer, it's acceptable for all the years. Okay, in the earlier years, they tend to word it differently, where they say sum of potential and kinetic energy of molecules in the system which are in random motion and randomly distributed. Okay, or sum of all random and microscopic potential and the sum of all random and microscopic PE and KE of all molecules in the body. They're still talking about the same thing. All right. Okay, now if you look at B is the one that you need to look at. The variation with volume V or the pressure P of an ideal gas as it undergoes cycle ABCA of changes is as shown. Again, you see there's a keyword ideal gas here. All right. So they tell you the temperature of the gas at A is 290 Kelvin and the temperature at B is 870 Kelvin. Okay, temperature at B is 870 Kelvin. Okay, so this one is 870 Kelvin. Okay, so from there, they ask you to determine a few things. Do you guys have the first few the first few questions? Yes, you have. Okay, so we have part 1 and part 2 in your worksheet. They ask you for start, determine the amount in mole of the gas. Okay, this one you can actually again still use PV equals to nRT following what you've learned in chemistry. You can either use point A or you can either use point B because you have the information for both A and B. It doesn't matter which one you use. Either you use point A or either you use point B. So over here, if I'm using point A, I know the pressure is 1.2 times 10 power 5. The volume is 4 times 10 power minus 3 meter cube. The molar gas constant is 8.31. The temperature in Kelvin is 290. So I can easily find the number of moles as 0.199 mole. Okay. You can likewise repeat the same thing for point B lah. Okay, so I know the values for point A. I also know the values for point B. So just do whichever you like. Either one will do. Okay, then the last thing they'll ask you is to find out the temperature of the gas in C. Okay. Again, you can still use PV equals to nRT. All right. You know the pressure. Point C is here. This one. You know the pressure. You also know the volume. Okay, you know the pressure, you know the volume. What you want to find is the temperature. Okay. Now at the same time, you also know the number of moles. Okay. Because you see your system is undergoing a closed cycle like this. It's a closed system. No gas was actually added, no gas was actually removed. So the number of moles should remain the same. The amount of gas remains the same. So if before this you already found out the mole of gas at point A or point B, it will also be the same at point C, okay? Because it's a closed system. So all you just need to do is to sub in your equations, PV equals to nRT. Eventually, you'll be able to find out what is T. T is actually 562 Kelvin. Okay, right? So this one is okay. Now, C is the one that's directly related to what you just learned. Explain why the change from C to A actually involves external work and a change in internal energy. So if you look back at your graph, it actually looked like this originally, right? It looked like this. Okay, it goes from A to B to C. So they're asking you right now, why is it that when you go from C to A, there's actually external work and there's actually change in internal energy? Okay. Now your graph here was actually a pressure volume graph. All right. So what are the few things that we've learned so far? Now we already know that for ideal gas, IE is proportional to temperature. This one I wrote a long derivation here just now for the previous questions. So ideal gas, we already know that internal energy is proportional to temperature. Now you see from C to A, did the temperature change? It did change, didn't it? This one is actually 562 Kelvin. This one is actually 290 Kelvin. So from here, we know that since T changes, therefore IE changes. Okay, so this one is first one. And then the second thing we ought to be able to say is, what about work? Okay, now we know that work done for gas depends on volume because of this equation. W equals to pressure times change in volume. Work done is actually dependent on any kind of changes in volume. Okay, it goes without saying the pressure must be constant here, right? So if you look at from C to A, there's actually change in volume at constant pressure. Okay, so here I can actually say that since volume changes, therefore there is work done. Okay, all right. Okay, now they just really want you to state whether is there any external work or not. Okay, you don't really need to go extra step to explain whether is work being done on the system or whether work is being done by the system. The same also goes with the changes in internal energy. You actually don't really need to explain whether is the internal energy increasing or decreasing. Okay, because if you want to go a bit more detail, which is unnecessary here, this one you could have said that from 562 Kelvin to 290 Kelvin, T is dropping, internal energy is dropping. But this one is actually not necessary lah. The question just says, state whether there's any change in internal energy. You're not required to explain what's the nature of the change, whether it's increasing or decreasing. Okay. And then likewise for the external work part, they just want to know whether is there any work done. They're not really that concerned whether it's work done on the gas or by the gas. But if you want to be again more particular, more detailed in this, you could also say something like this, because you see your volume is decreasing, you see, volume decreases, work is done on gas. Okay. So the only thing you can probably just say here is that delta W is positive, no? According to thermodynamic first law. Okay, but again, this one is actually not necessary. You don't need to explain until this detail. What you just need to do is to explain whether are there changes or not. So what were the changes dependent on? That's why your answer was written like this. Because there's temperature change. Because there's temperature change, internal energy change. And then after that, the second one is that because there's volume change at constant pressure, so external work is done. That's all there is to it. Okay, you don't need to explain all the way to the nature of the change. All right. Okay, so this one is done. We have page 3. Okay, page 3 is probably the last one. Then after that, I think we can take a short break. Okay, so have a look at page 3. Hey, wait a minute. Am I looking at the correct thing? Oh, it's page 7. Sorry. My mistake. Page 7. Okay. Have a look at page 7. This one is actually a qualitative description of stuff. Can you guys have a look at page 7? All right. So this is November 15, P41. Okay, so for this one, state an expression in terms of work done and heating that is used to calculate increase in internal energy of a system. So how is increase in internal energy related to work done and heating? This one by right, you should know it is actually already relating to thermodynamic first law, which is summarized by this equation. Okay, which tells you that increase in internal energy is equal to heat energy supplied to system and work done on the system. Already you can just say plus work done on the system. Okay. Now, whether or not do you really need to write all these variables here, you don't really need to write this now. Okay. It's just that here I wrote it as something like an extra. You don't really need to write these variables and the equation here. You can just write it fully in words. Okay. So this is one. Okay, so this one is done. Then after that, you look at the second part, part B. Okay. Now, for the second part, state and explain in terms of your expression in A, the change, if any, in the internal energy of, say, water in an ice cube when ice melts and atmospheric pressure to form liquid without any change in temperature. Okay, now, your case here is that when you are talking about internal energy, there's actually two ways to explain changes in internal energy. Okay, the first one was based on this, where you say that internal energy is equals to Ke plus Pe. From here, we can say that change in internal energy is equals to the changes in any kinetic energy plus changes in any potential energy of the molecules. This one is one way to explain changes in internal energy. There's also another way to explain changes in internal energy, which is this one. Which is this one here. Okay, this is another one. All right, there are actually two ways to explain changes in internal energy. All right, which one you want to use actually depends on the context of the question. This one, the first one you see, is actually from definition of internal energy. The second one here is actually from thermodynamic first law. Okay, so your question here actually already told you to use the expression in A, which is actually this one. Okay, the question already specifically told you to use the expression in A, which is actually first law of thermodynamics. So whatever explanation that you use to explain changes in internal energy, it should be based on thermodynamic first law, where you try to explain whether heat is supplied or not, whether work is done on the system or by the system. Okay, so this is what you need to see here. All right. Okay, so how are we going to explain this? Now, there's one thing I need to explain first before we go any further. Now, if I talk to you about ice, and then it changes to, say, water, like this. If I tell you that the ice is 1 kg, your water will also be 1 kg, right? Correct? But at the same time, we know that the point I want to make here is this. Is the volume of ice going to be the same as volume of water when it melts? The answer is no, actually. All right. The mass, it remains the same. Now that's correct. The mass remains the same. The density would change. Okay. The density changes. Okay. So when ice changes to water, the mass actually remains the same. The density would change. The volume of the water, so the volume between ice and water would actually be different. Okay, they're not going to be the same. All right. But what is the volume? I mean, which is going to be having the larger volume here? All right. So one way of seeing this is by using this equation from AS. Now, we know that density is mass over volume, right? Now, so I mentioned to you that when you have ice and you have water, ice melts to water, the mass actually remains unchanged. Mass is constant. Therefore, rho is inversely proportional to volume. Okay, so that's what we know. Now, then after that, what do we know between ice and water? Which one is going to be having a larger density? Which one is going to be having a lesser density? This one, you can actually think of it this way. Ice floats on water, right? Therefore, density of ice is less than density of water, okay, in the first place. So from here, from the case where rho is inversely proportional to 1 over volume, sorry, is inversely proportional to the volume. If your density increases, your volume decreases, right? This one is when ice changes to water. Okay, when ice changes to water, the density will increase. All right. So when density increase, volume decrease, no? Okay. So you just bear this in mind first, because we need to use this to explain the work done. Okay. So when you want to explain the changes in internal energy of water melting in when you want to explain the change in energy of an ice melting into water, according to thermodynamic first law, you need to explain based on the heat supply as well as work done. Okay, so now I'm trying to explain to you based on the work done first. Okay, so you're talking about the work done. The first thing you could have probably said is this: when ice melts to water, the volume decreases, so work done is on the system. Okay, so work is done on the system. This one, let's just say, is number one first now. Okay, the volume decreases, so work is done on system. Delta W is positive. Okay, then the second statement, you probably need to talk about the heat supply. That one will be this one. Now, when you want to let the ice melt into water, you obviously need to absorb thermal energy in order to break the lattice structure, right? So therefore, you have positive delta Q. Okay, you really only need these two statements that I just labeled in red here for you. First, you say volume decreases, so work is done on the system, delta W is positive. The second one is thermal energy will be absorbed to break the lattice structure. U or delta Q is also positive. Okay, so if you look at the definition of thermodynamic first law, let me just get rid of some of this. If your work done was positive, and then your heat is also positive, wouldn't this tell you that delta U is positive? So therefore, is internal energy increasing, isn't it? Right? So you are basically trying to single out what is the work done, what is the heat supply first. Only then can you determine what is the internal energy change. So your answer is supposed to focus on those two. All right. You need to say statement number one, you need to say statement number two. Okay. Now, there's also another different way of explaining the work done. That sometimes people will also say this: when ice changes to water, this one is another way of explaining the same thing. When ice changes to water, sometimes people will just say that you have negligible volume change. Okay. So when you have negligible volume change, delta W is 0. Okay. This one is all. Okay. This is another different way of thinking about it. which is actually what is written in pencil here. Okay. If you're talking about the work done and then you relate to the volume, either you say the volume decreases, so work is done on system, or either you say there is negligible or only a small change in volume, so work done is negligible. Okay, you can also say this. All right, usually for your thermal properties chapter, for the past year exam questions that talk about ice melting into water, the volume change is, you can have two different answers for the volume change. Either you explain it as volume decreases, or your volume change is negligible. Okay, the marking scheme will always accept either one. Okay, either you say volume is decreasing, so work done on the system, or you say that volume change is negligible, so no work done on the system. Okay, so both answers are actually acceptable. Okay, so this one I'll probably just write this one. This one is number 3 instead of 1. Okay, you could also write this if you wanted to. Now, even if you write number 3, where you say there's only negligible volume change, so work done is actually 0, you actually get back the same conclusion. Why do I say this? Is because if work done is 0, this one is neither positive nor negative, but you still have heat supply to break the lattice structure so that your ice can melt. So if this one is 0, this one is positive, internal energy is still going to be positive. So you're still going to get the same conclusion that internal energy is increasing. Okay. So it actually doesn't matter. Okay, both will still give you back that same conclusion. Okay. Right. So this one is okay. Then after that, I go through the last one for you. Okay, now the last one is this one, where they tell you what is the change in internal energy of gas in a tire when the tire bursts so that the gas suddenly increases in volume. Assume that your gas is ideal in the first place. Okay, so again, same thing. You're supposed to explain it based on internal energy. You're supposed to explain it based on thermodynamic first law. You need to single out what's the work done. You need to single out what is the thermal energy. Okay, so in your case, this one you probably have to do it like this. Let me just draw it somewhere. Okay, so the situation that is described here is this. You have, say, a tire. This tire contains a volume of gas. This is your gas right now. Okay. Somehow or another, your tire suddenly bursts at some point. Okay, your tire suddenly bursts. There's a hole inside your tire. Okay, say maybe something like this. There's a hole here. Okay, because your tire suddenly bursts. So now your gas that is originally contained inside your tire will now start to escape. Okay, so now this is what's happening to your air inside your tire right now. Okay, now from here, if you try to look at the volume change, when you go from here to here, because your air is already escaping, your volume of your air is actually increasing. So you can actually say that work is done by gas. Therefore, delta W is negative. Okay. So this one is number 1. Then another thing here is the keyword that your question mentioned here. Now, the question mentioned that when the tire bursts, the gas suddenly increase in volume. So what you're supposed to deduce from here is that This one is too sudden for any maybe I should use a different color. Let me just erase this. Sorry. The keyword here, when they say it suddenly increases in volume, you can just take it as is too sudden for any heat energy to enter. Too sudden for any heat energy to be absorbed or released by the system. Okay. So therefore, delta Q is 0. Okay. So from here, you can actually see this. If you want to explain it in terms of work done, the volume is increasing where it's done by gas. So delta W is negative. But then when you go and single out the heat supply, because they say that the thing happened too suddenly, it's actually too sudden for any heat energy to be absorbed or released by the system. So delta Q by right would be 0. So you try to use thermodynamics first law to deduce the change in internal energy. You look at this one here, maybe I better write it at the top. If I say that delta U is delta Q plus delta W, my work done is negative. My work done is negative. My heat supply is 0. So my internal energy is negative. It's going to be a decrease. Okay. So you could say that your internal energy is decreasing. Okay. But look at your answer. The answer that's written in pencil again is slightly different. This one, it was stated here that the gas expands against the atmosphere. So what is done by the gas? Okay. So if you wanted to, you could have probably just replace it with the explanation here like this. This one is actually easier to understand for most people, I notice. The gas is expanding, volume is increasing, so work is done by the gas. Here, I'm actually saying that the gas is expanding against the atmosphere. This one is actually implying volume increasing. And this one in itself is actually implying volume increases. Okay, gas expands against the atmosphere. This is implying volume increases. So work is done by gas. But if you wanted to, you can actually just directly write that the volume is increasing as it expands against the atmosphere. So work is done by gas, delta W is negative. Okay. The second statement, that one I think is pretty straightforward. This one is saying that there's no time for thermal energy to enter and leave the gas. Therefore, delta Q is 0. So from here, internal energy decreases. Okay. Now in the marking scheme, they never really needed you to explain whether your delta Q is positive, delta W is 0, or delta W is negative. Okay. The marking scheme itself did not require you to specifically state whether the delta W or delta Q is positive or negative. Okay. But I noticed that it's actually easier for a lot of people if you just write it down because it helps you to understand the answer better. Okay. Right. So just bear in mind that whether or not the delta Q or delta W is going to be positive or negative, the answer never, the marking scheme never specifically wrote it inside. Okay. But I would say that if you write it in, it helps you to understand your answer better. Okay, so you can actually write it in. Okay, although it's not required by your marking scheme, but I would suggest that you write it in because it helps you to understand your answer better. The workings that I have here written in pencil originally didn't have the explanation whether it's positive delta Q or positive delta W, but just write it lah. Okay. Right, so that one should be okay. Yeah, so you see, I will write the delta Q, delta W, whether it's positive, negative at the side. All right. Okay, right. So I think this one should be okay. We've gone through enough questions on thermodynamic first law. Right. The next one that I can go through is actually page 14, but this one is actually related to something else. Okay. Okay, there's another question that you can actually see later on. This one is page 14. You will notice that this question in page 14 is actually similar to that in page 7, which you just done. It's just that the wordings are slightly different, but they're still talking about the same concept. Okay, so the one in page 14, you can probably do it as something like your homework. Okay, because it's still talking about the same thing as page 7. All right. Okay, right. If you look at page 5 of your notes, we already did page 4, which is thermodynamic first law. Look at page 5 of your notes. Okay. Now, in IGCSE or SPM last time, you may have learned the concept of specific heat capacity and specific latent heat. Okay, we know specific heat capacity or specific latent heat as being related to how much heat energy needs to be absorbed in order to cause 1 degree in temperature rise, or how much heat energy needs to be absorbed in order to cause the phase change of a substance in general. Okay, so your syllabus requires you to know these two quantities. Okay, the definition will come out and calculations related to it will also come out. Okay, so let's just start with some of the basic definitions. So you would have learned what is heat capacity before. Heat capacity is just simply heat energy needed per unit temperature rise. How much heat energy is required to cause 1 degree centigrade temperature rise or 1 Kelvin temperature rise. Okay, in equation form, it's probably just written as C equals to heat supply divided by your temperature change. Okay. Now, the one that's actually more useful a lot of times is specific heat capacity. Okay. Right. The only difference between the first and second one here is the term specific. All right. So when you have the term specific heat capacity, it is heat energy needed per unit mass, per unit temperature rise. Okay, the word specific already implies per unit mass. Okay, this is a more useful quantity that we are interested in. We want to know how much heat energy must 1 kg of material absorb in order to cause the temperature to increase by 1 Kelvin. So last time you probably learned it as this, where we say Q is MC delta T. So if you go and make C the subject, you're going to get Q equals to M. You're going to get C equals to Q over M delta T. This is the more common one that you've always been using. All right. Okay. Now, then we move on to the concept of latent heat. Latent heat is just simply the heat energy required to change the phase of a substance at constant temperature. When you're talking about the phase of a substance, you have 3 different phases: solid to liquid, and then liquid to gas. It can also go the other way around, all right? So the thing is that when you change between these 3 different phases, you need heat energy, okay? Either heat energy will be absorbed or either heat energy will be released. If you're going in this direction, heat must be absorbed. But if you're going in this direction, heat must be released. Okay, so latent heat is just simply heat energy required to change the phase of a substance at constant temperature. All right, now you could have more specific terms for latent heat also, namely latent heat of fusion or latent heat of vaporization. If we say latent heat of fusion, it is the heat energy required to change the phase of a substance from solid to liquid at constant temperature. Okay, the word fusion here already means phase change from solid to liquid. Now, on the other hand, if you have latent heat or vaporization, it is heat energy required to change the phase of a substance from liquid to gas at constant temperature. So the word vaporization here already implies phase change from liquid to gas. Okay, so this is latent heat. Now, there's also another different set of definitions that relates to latent heat. This one is specific latent heat. Okay, again, the only difference now is the addition of the term called latent. The only difference now is the addition of a term called specific. Right? When you have the term specific, it just means per unit mass. That's all. Okay, so your definitions for specific latent heat, specific latent heat of fusion, specific latent heat of vaporization, they will all be the same as before, just that it is all per unit mass right now. Okay, that's the only difference. So in general, if you want to find out what is specific latent heat, you just take the heat energy that has been supplied to cause the phase change divided by the mass that has changed phase. This one will give you your specific latent heat. All right. Okay, now, sometimes your question may also ask you, why is it that specific latent heat of vaporization, generally more than the specific latent heat of fusion? Okay, why does it take more heat to vaporize a substance as compared to melting a substance? Okay, so sometimes they might ask you this in your question. Why is it that generally specific latent of vaporization is more than that of fusion? Why does it require more heat energy in the first place to cause a phase change? So you can consider this when you're talking about liquid changing to vapor or gas. When you're talking about liquid changing to gas, the phase change from liquid to vapor involves a large increase in volume compared to that of solid to liquid. Okay, liquid to gas, you would have a larger increase in separation of your molecules, so you have larger increase in volume. So when you have larger increase in your volume, larger increase in your separation, this already tells you you will have larger increase in molecular potential energy. You need to increase your molecular potential energy even more when you go and change from liquid to vapor. Okay, this is point number one. Large increase in volume, larger increase in molecular PE. So you need more energy here. And then after that, another thing that you can also talk about is that when your liquid changes to gas, the gas has to expand against the pressure of the atmosphere. Right? So this one involves you doing more work. Your gas needs to do more work here. It has to take energy from something, which in your case comes from the heat. All right. So when you have larger increase in volume and you need to do work against the atmosphere, this one already causes your phase change to require even more energy. Okay, that's why we tell you specific latent heat of vaporization generally will be greater than that of latent heat of fusion, specific latent heat of fusion. Namely because number one, larger increase in volume. Number two, you have to do work against the atmosphere. Okay, so this is one thing to note. Okay, now you also would need to know how to determine by experiment specific latent heat and specific heat capacity. So we start with specific heat capacity first for solid and liquid. All right. So let's just say that right now we want to determine specific heat capacity for, say, a piece of metal. All right. So generally, what we do is that if we know that Q is equals to MC delta theta, when we have specific heat capacity we want to find, we generally want to find out the heat supply, the mass of the substance, as well as the temperature rise, isn't it? We need to know the heat supply, we need to know the mass, and then we need to know the temperature rise. Okay, these are some of the things that we need to find out. So say right now, I want to find out the specific heat capacity of a block of metal. All right. So what I'll do is that I'll arrange the metal in a manner similar to this apparatus. So I'll make sure that that metal has holes inside it so that I can put a thermometer and an electrical heater. Okay, so that block has mass M here. Okay, so this mass M I can actually measure using my mass balance. All right, now what is the purpose of your thermometer and your electrical immersion heater? So it goes without saying that your electrical immersion heater here is meant to provide heat energy to the block. It's meant to heat up the block. Okay, and then your thermometer is meant to measure the temperature rise of the block. All right, and then when you have a metal block here and you heat it up, you're supposed to insulate it with, say, maybe polystyrene, so that you can minimize heat losses to the surroundings. Okay, and when you are trying to heat it up, remember just now you had holes between your for you to put in your heater as well as your thermometer. So usually when you put in your heater and your thermometer, it won't be a perfect fit. It will be some loose fit there. So you would put oil in between the gaps, or rather you just put oil inside the holes so that you can have good thermal contacts between the heater, metal block, and the thermometer. Okay, so you switch on before you switch on your heater, before you heat up your metal block, you need to measure the initial temperature T1 of your block. Okay, and then after that you close your switch so that heating can begin. All right, now when you close your switch so that heating can begin, you're interested to find out how much heat energy has been supplied to the block. Okay, so there's a reason why we use an electrical way of heating your block, is so that we can easily calculate out the energy, the heat energy supply. If you remember that in your in your current electricity in AS physics, remember we tell you that power is VI, and then power is energy over time equals VI here. So energy is VIT, right? So the reason why we want to use an electrical method of heating your block is so that we can easily calculate out the heat energy that has been supplied. If we know the voltage across your heater and the current flowing through your heater, we can easily find out the amount of electrical energy that has been supplied. All right, that's the reason why we need to find out the current and potential difference in the first place by using an ammeter and voltmeter. Okay, so we continue heating it until we continue heating the block for a time t. We continue heating the block for a given time t, such that you have a substantial temperature rise. Then after that, you measure the final temperature of the block. Okay, now from there, you can then apply conservation of energy, which tells you that whatever electrical energy has been supplied by your heater would be equal to the heat gain by your block plus any heat loss to the surrounding. Okay, this is the actual energy equation following conservation of energy. So you write it in equation form, you will get VIT equals to MC T2 minus T1. Okay, so VIT just now I explained is this one, is meant to find out is the electrical energy supplied by your heater. Then MC delta T is basically your heat gain by your block. All right, H here is your heat loss. Okay, now a lot of times if your insulation is really good, is really thick, so that your heat loss is very, very small, so that it's negligible, you can actually ignore H here. Okay, so if you ignore H here, the equation becomes VIT equals to MC delta T. So you can find out V, you can find out I, you can find out T, you can find out M, you can find out delta T. Then after that, you can find out C easily. Okay, so this equation here, if your insulation is very good to the point that heat loss is very small to the point it is negligible, you can just ignore this term. And then after that, you can straight away find out what is your C. Okay, but if you do that, usually you won't get an accurate answer. I mean, is an approximation, but not as accurate as you would like it to be, because heat loss is still there, just that you ignore it. All right. So one of the things that they will normally ask you is this. They will ask you, if you ignore the heat loss in order to find the specific heat capacity, does this lead to an overestimation or an underestimation of your value of C? Okay, if you ignore the heat loss to find out what is your C in the first place, would it cause you to get an overestimation or underestimation of the true value of C? Are you going to be getting a value that is higher than the real value or lower than the real value? So the answer is that you will always get an overestimation of your value of C if you ignore heat loss. Now, the reason for that is because of this. One way to understand it is by this. Okay, let me just erase all certain things. Let's just say that under the ideal case, no heat loss, what would happen is this. If this is your block, if you supply 100 joules of energy, heat energy, your block will gain 100 joules. Okay, this one is the ideal case, no heat loss. You assume that whatever heat energy that your heater is supplying is fully absorbed by your block. But if you consider the real case, the actual case, with heat loss, you still have the same block, you still have, say, the same amount of energy supplied by your heater. But the thing is that if you supply 100 joules of energy by your heater, if your heater supplies 100 joules of energy, your block isn't going to get that full 100 joules of energy. Maybe it could be getting 80 joules. And then the rest of the 20 joules is actually lost to surroundings. Okay, so your actual case is that you're actually getting less heat. But the thing is that when you ignore heat loss, you're assuming that your block is getting all the heat. So when you ignore heat loss, the heat absorbed is assumed larger. Therefore, C is an overestimate. Okay. Because by right, if you're talking about the actual case right now, you supply 100 joules, your block is actually just taking 80 joules, and then the 20 joules is lost. But then when you ignore heat loss, you assume, oh, this one is not present. That would mean that whatever energy supplied by your heater is actually fully absorbed by your block. So your heat absorbed is actually assumed to be larger. Therefore, your C will be an overestimate. An easier way to look at it is to look at this equation. C is equal to Q M delta T. If your heat is now assumed larger, heat absorbed is not assumed larger because heat loss is ignored, your C obviously will be larger. Okay, so that is the understanding behind this. Why is an overestimate? But you won't be asked to explain why is an overestimation. Okay, you are really just required to know, if we ignore heat loss, what does this cause our calculated C to be? It will just be higher than the real value. It will just be an overestimate. That's all. Okay, so this is how you find specific heat capacity for a solid. Okay, then after that, we move on to finding specific heat capacity for a liquid. All right, now to find specific heat capacity for a liquid, it is generally the same as that of a solid. Okay, just that you need to make some adjustments. Now, you know that liquid doesn't have any fixed shape or form, right? So it cannot stand by itself. So you normally need to contain it inside a liquid, isn't it? You normally need to contain it inside a container, right? So when you want to find out the specific heat capacity of a liquid, you need to put it inside some sort of container in the first place in order to hold the liquid inside. So here, the only changes you will make compared to that of a solid is that you would have the addition of a container inside, that's all right? So here you have, say, a liquid of mass m that's contained inside a calorimeter. This is your container, which is made from polished copper or aluminium, and then it's also insulated to minimize any heat loss. Okay, now your container that is used to hold the liquid would have its own mass as well as specific heat capacity. Okay, your container actually would have a stirrer along with it. Okay, the purpose of the stirrer, which is this little thing here, is actually to stir your liquid during heating so that you have even heat distribution. Okay, so your calorimeter and stirrer is assumed to be made of the same material, so they will have same specific capacity, and then they all have their own masses. Okay, so they have their own mass, they have their own specific capacity. When you want to find out the specific capacity of your liquid, you do it like you would the solid. You will need to heat it up using your electrical heater. Make sure you find out the current and voltage across the heater so that you can find out the heat energy supply. And then after that, you go and measure the temperature rise before and after heating for a time of T. So you go and apply conservation of energy, same like before, you're going to get something similar where we say that electrical energy supplied by heater is equals to the heat gained by the liquid plus heat gained by calorimeter and stirrer plus any heat loss. Okay, so this is the energy equation. When you try to write it out with symbols, mathematical symbols, you will get VIT equals to MC delta T for liquid, and then MC delta T for calorimeter and stirrer. And then not forgetting your heat loss. Okay, so same thing again. If you want to find out the specific heat capacity of your liquid, you can just say that if your insulation is very thick, your heat loss will be very small to the point that it is negligible. So when your heat loss is negligible, it's assumed negligible, you can then find out what is C, assuming that you know everything else inside here. Okay, but same thing as before, the moment you do this, you're going to get the value of C that is an overestimate, which is larger than your true value. Okay, so that's the only thing you need to know when it comes to finding specific heat capacity for a liquid. All right. Okay, there's also determining latent heat, but this one I think is pretty long. It'll probably be done in the next lesson. Let's just do some questions first, all right? Okay, there's two questions that we can probably do for now. One is page 21, one is page 18. Let's go through these two, right? Okay, so can you guys just have a look at page 21? Okay, have a look at page 21. Just look at page 21 first. Okay, this is June 18 P42. Okay, so look at page 21, June 2018 P42. Now, question 3A. They're telling you right now that during melting, a solid becomes a liquid with little or no changes in volume. Use kinetic theory to explain why during the melting process, thermal energy is required, although there's no change in temperature. Okay. Now, this one here, they say use kinetic theory to explain why during melting process, the thermal energy is required, although there's no change in temperature. Kinetic theory here refers to the fact that matter is composed of many small particles that are in constant motion. This is what kinetic theory of matter is. Okay, it is saying to you that any matter, solid, liquid, or gas is actually just made out of many small particles that are always moving. Okay, so here they're asking you to explain based on that point of view, explaining it based on based on the molecules. Okay, basically they're asking you to explain based on the molecules. By looking at how the molecules behave, explain why when you're melting ice, for example, you need thermal energy, but there's no change in temperature in the first place. Okay, so this one you can actually kind of explain it in two different ways. The marking scheme has one way to explain it, but there's also another way to explain it too, based on what you've done so far. Okay, this one I'll go through the one that's not in the marking scheme one first, the one that is more towards what you've done so far. Now, how do I explain that when I melt something, I only need heat energy, but the heat energy won't cause any change in temperature? Okay, so there's this common misconception among students that they always think that, oh, if you supply heat energy, temperature must change. This is not true. If you think about when you're trying to melt something, when you go and melt something, your object, when you're trying to melt something, for example, you're supplying heat to melt the object. When it melts at this melting point, the temperature remains constant, isn't it? But you're still supplying heat. Or another way to think about it would be when you're boiling water, say, for example, you go and supply heat to boil water, the water boils, but the temperature doesn't change, right? At the same time, you're still continuously supplying heat to it, isn't it? So this is already proof that when you go and supply heat, it doesn't necessarily cause a temperature change, okay? Right? So when you supply heat, temperature can change, but at the same time, it can also not change, okay? It works both ways, all right? Just because you have heat supply, it does not necessarily mean that your temperature will change. You just look at your melting point and boiling point. Those cases, you are supplying heat, but your temperature will never change, okay? So their question here is actually trying to ask you about that. Why is it that I can be supplying heat to something, but there's actually no change in temperature? They are trying to ask you to explain that, okay? So you can actually look at it from one way, based on your definition of internal energy. Remember I told you that internal energy is actually your kinetic energy plus potential energy. So that any changes in internal energy is just simply the change in kinetic energy plus potential energy. Now, if you had no change in temperature, temperature is constant, the change in kinetic energy will be zero. So whatever change in internal energy would just be the change in molecular potential energy. Okay, so recall that earlier I also mentioned to you that kinetic energy is proportional to temperature. So your T is constant, your Ke is constant too. Okay, that's why I can say this over here. Your change in Ke is zero. So whatever change in internal energy you have will be due to the change in molecular potential energy. Okay, this one again is from definition of internal energy. And then after that, you can try to relate to first law of thermodynamics. Okay, you can, then after that, you can relate to thermodynamic first law, which tells you that the increase in internal energy is equals to the work done in the system plus heat supply to the system. Okay, now, when you melt something, they already told you a solid tends to become a liquid with little to no change in volume. Let's just talk about the part where it has no change in volume. Now, when you do not have any changes in volume, you do not have any work done. So this one here would be gone already. So your change in internal energy, or rather your increase in internal energy, is actually equal to your heat supply. So you look at this one. If I tell you that this one is equation 1, and then I tell you that this is equation 2. If you combine them together, aren't you going to get delta Q equals to change in your PE? Okay, so in your case, if you supply heat to your system, your PE is going to increase. Okay, so just bear this in mind first, right? Why do I need to say this? Is because of what the answer here wrote. You see, when you melt something, the bonds between atoms are broken. So the potential energy of your molecules is going to be increased. Okay, so if you relate it to this one, I mean, if you understand this first point here first, when you melt something, bonds between atoms must be broken, so the molecular potential energy is increased. Okay, so if your molecular potential energy increase, you must have heat supply. Okay, that's what this thing is trying. That's one way of looking at it right now. Okay, during melting, the bonds between atoms are broken, so potential energy of the molecules is increased. When potential energy of molecules is increased, you would have heat supply. You need to have heat supply. Okay, this one explains to you why you need energy, thermal energy in the first place, although you do not have any change in temperature. Okay, because in the first place, when you go and melt something, its potential energy must increase. And the potential energy increase must have come from the heat supply. Okay, this is one way of looking at it. Okay, now there's also another different way of doing this. This one is actually based on the marking scheme answer that's written in pencil here. Okay, so if you base on the marking scheme wrote it like this. You still have the same first point where they tell you during melting, bonds between atoms must be broken, so potential energy of the atoms is increased. The molecular potential energy is increasing. Okay, now when you want to have your molecular potential energy increase, it could have come from two things. Okay, so this one, understand that bonds broken, molecular potential energy increase. When molecular potential energy increase, the only way it can increase could have been two ways only. Either is through work done or either is through heat supply. Okay, but we already know that there's no change in volume. So since there's no volume change, there obviously is no work done. So in your case, this one is out. The only way that your potential energy could have increased is through heat supply. Okay, so that's why your answer is written as this. You would need to say that, okay, in the first place, there's no change in volume, no work is done. Thus, the required input energy must have been from thermal energy. Because in the first place, your potential energy increase must have come from something. If you already established that it did not come from your work done, it must have come from your thermal energy supply instead. Okay? So this is actually what the marking scheme wrote. It's based on this understanding here. Okay? But you can also explain it another way through definition of internal energy and thermodynamic first law. But this is actually, I think, a bit more tedious. That's why they never use this at all. But this is what we've always been using for your previous question. So if you've done a lot of it, sometimes you tend to use this to explain. Okay, but marking scheme but the current marking scheme is using a different way. Okay, just so you know. Okay, so if this one is okay, then I go on to some questions that relate to heating and phase change. Okay, right. So let's have a look at the bottom part of your current question. Now here, you have an aluminum can of mass 160 grams that contains a mass of 330 grams of warm water at a temperature of 38 degrees as illustrated in the figure. You have a mass of 48 grams of ice at negative 18 degrees centigrade that's taken from a freezer and put inside the water. So the ice melts and the final temperature of the can and its contents is 23 degrees centigrade. So data for the specific capacity C of aluminium, ice, and water are given in the table below. All right. Then they ask you, assuming that there's no exchange of thermal energy with the surroundings. This one is actually telling you there is no heat loss. Okay, assume no heat loss to surroundings. So once you assume no heat loss to the surroundings, they want you to show that the loss in thermal energy of the can and warm water is 2.3 times 10 power minus 4 joules. Show that this is the amount of thermal energy loss from both can and warm water. Okay. All right, now before we proceed, let's just try and look at the diagram a little. Now, one thing that you need to understand first is this. When it comes to heat energy always flows from higher temperature to lower temperature. Okay, this is a known fact. Heat will always flow from any object with higher temperature to a lower temperature. Okay, so in your case, you look at your current diagram, you actually have three things to consider. Aluminum can and warm water, both at temperature 38 degrees. And then after that, you have ice at negative 18 degrees. So if you look at your aluminum can right now, it is at 38 degrees and your warm water is at 38 degrees. And then your ice is at negative 18 degrees. This is the initial one. So from here, if you know that heat energy always tends to flow from higher temperature to lower temperature, what you can actually say is that heat energy actually is flowing into the ice right now. This is the direction of flow of heat energy. Because ice is at negative 18, but aluminum can and warm water are both at 38. So heat energy will actually flow from the can and warm water into ice. Okay, so in your case, when heat energy flows inside the ice, you would then say that, oh, your aluminum can must therefore be losing heat energy, then the temperature will drop. And then the same thing goes for your warm water also. It must be losing heat energy, and then the temperature will drop. So it just so happens that the temperature that they drop to eventually will be 28 degrees centigrade. The question already told you the ice melts and the final temperature of everything will be 23 degrees. Okay, so you see this is what's happening for your aluminum can and for your warm water. They are both losing heat energy. The temperature drops from 38 degrees to 23 degrees. And then when you look at the ice, because heat energy is flowing into it, its temperature will increase from negative 18 degrees to 23 degrees. It's gaining heat energy here. Okay, so this is what you can kind of see happening right now. So the question is asking you, what was the heat energy lost by the warm water and aluminum can? Okay, so you see for both these cases, you can actually just use the general equation. Q is mc delta T. You know the temperature change, you know the specific heat capacity, and you also know the mass of both of these objects. So you use Q equals to mc delta T for both the can and warm water. This is what you're supposed to be getting. Okay. So just use mc delta T for the aluminum can and the water. Just sub in your values. You will eventually get the answer as 2.3 times 10 power 4 joules. Okay. Now you just take for the temperature difference, you just take the larger value minus the lower value. Okay, you don't need to bother about whether it's initial minus final temperature or final minus initial temperature. We generally do not want any negative. Just find the difference in the magnitude, which means just take the larger minus the smaller value. Okay, So aluminum can is 160 grams, specific capacity is 0.91. There's no need to change from kg to gram. There's no need to change from gram to kg here because you see your specific heat capacity is in grams per grams. So if you use the mass in grams and then you multiply with specific heat capacity, the gram will cancel off. So no need to change the units. Okay. So just sum in the values and you will eventually get your answer as 2.3 times 10 power 4 joules. Okay. Right, so this one should be okay. Okay, then after that, last one. Use the information in one, which is this one, to calculate a value L for the specific latent heat of fusion of ice. What is the specific latent heat of fusion of ice? Now, based on what I just explained to you over here, if you try to use conservation of energy, it is correct to say that whatever heat energy was gained by the ice is actually equal to whatever heat was lost by the aluminum can and warm water, right? So whatever heat was lost by these two, by the can and warm water, would have been the heat gained by the ice in the first place, okay? So they're asking you to find out the specific heat, latent heat of fusion of ice, which is this part here, which should be for this part here, okay? Now, heat lost by the can and water will be heat gained by ice. You see this equation here that is written, this equation here that is first written here. This one, the Q loss is actually from here. And then all this little expression that you have here is actually the heat gain by the ice. Okay, but you notice that there seems to be quite a number of terms. You somehow have Q equals to MC delta T, and then you also have Q equals to ML. All right, now the reason why it's like this is because you need to look at how the ice melted into water in the first place. There's actually some phase changes involved and some temperature changes involved for two different phases. What I mean by that is, remember you start off with ice at negative 18 degrees. It is actually a solid, but then after that you need to have the temperature increase to 0 degrees while it's still at solid. So this one will be MC delta T. Then after that, when your ice is at 0 degrees and is still a solid, it will now need to change to water at 0 degrees. Okay, so from solid to liquid at the same temperature, this one is actually latent heat. Okay, this is where your phase change occurs, right? So once your ice change to water at 0 degrees, is now in liquid form, it still needs to gain heat energy so that the temperature becomes 23 degrees while it's still at liquid form. So this one here, you will still need to use MC delta T. Okay, this part here is where you have phase change, and you have phase change here. Here to here you have phase change. Here to here, no phase change. Okay, now maybe I just say same phase now, so that it's easier to see. This one is same phase. This one is also same phase. Okay, for temperature changes involving same phase, you use MC delta T. But for phase change at constant temperature, here at melting point, you use ML. Okay, that's what you're seeing right over here right now. Okay, so from here, you just submit your values. Your heat loss originally, you established it as 2.3 times 10 power minus 4. And then what was the heat gain by the ice? It will be mass of ice times specific heat capacity of ice times the temperature difference. So same thing as before lah. I mentioned to you, just take the difference in the temperature. Don't bother about any negative. So you just be 18. And then after that, once you're having a phase change from ice to water, your mass is 48 grams. And then the L is what you want to find. You just take 48 times L. Okay, you don't need to change anything you don't need to change the units from gram to kg. Because you see this one is joules per gram. So you can just leave everything in grams. Okay. And then after that, the last term is after you change to liquid at 0 degrees, you still want to have a temperature increase to 23 degrees. Again, you use MC delta T. You still have the same mass of melted ice, multiply with the specific heat capacity of water now, multiply with the temperature difference from 0 to 23 degrees. So after that, try to simplify the algebra here, try to solve and find for L. You will eventually find out that L is 345 joules per gram. Okay, all right.